Recording in progress.
We are back and we're still continuing to go through the volume 2 of the DOE book. We talked about conduction, we talked about convection, or the different types of heat transfer. So today we're going to talk about radiant heat transfer. Radiant heat transfer is thermal energy transferred by means of electromagnetic waves or particles. And so in this chapter, we're going to describe how these terms relate to radiant heat transfer, such as black body radiation, such as emissivity, such as radiation configuration factor. And so in order to talk about, in order to get this started, we're going to talk about thermal radiation. Radiant heat transfer involves transfer of heat by electromagnetic radiation. And this arises due to the temperature of a body. And so most of the most energy of this type is in the infrared region. So of course, there are different regions for these sorts of waves, right? So you have visible light waves, and then on one end you have infrared, and on the opposite end you have UV-Vis. You also have gamma radiation. So this is infrared, the infrared region of the electromagnetic spectrum. And so the way you think about it is you think about waves, different types of waves of light, different types of waves of energy, and how at the center of that is the visible light. On one end, like I said, is infrared. And so the infrared region of this spectrum, it is in the visible spectrum, okay? Not necessarily to us, but to animals, okay? So animals that hunt at night are able to see infrared, all right? And so the term thermal radiation is frequently used to distinguish this form of electromagnetic radiation from other forms such as radio waves. We talked about how that's on that spectrum when we start talking about waves, X-rays, and gamma rays. The transfer of heat from a fireplace across the room in the line of sight is an example of radiant heat transfer. And like I said, there are certain animals that hunt at night that can see infrared, okay? So they can see heat from the other animals, and that helps them hunt. So radiant heat transfer does not need a medium, such as air or metal, to take place. Any material that has a temperature above 0 will give off some sort of radiant energy. And when a cloud covers the sun, both its heat and light diminish. This is one of the most familiar examples of heat transfer by thermal radiation. So black body radiation, a body that emits the maximum amount of heat for its absolute temperature, is called black body. And so radiant heat transfer rate from the black body to its surroundings is expressed by the equation Q is equal to sigma AT to the 4th power. So Q is the heat transfer rate in BTUs per hour. Sigma is the Stephen-Boltzmann constant, which is 0.174 BTU per hour foot squared. Rankine to the 4th power. A is the surface area, that's in feet squared, and temperature is in Rankine. So T is temperature, that's in degrees, which is one of the absolute scales. We're in volume 2. We are on page 26. Two black bodies that radiate heat towards each other have a net flux between them. The net flow rate of heat between them is given by adapting the aforementioned equation. So Q is equal to sigma A times T1 to the fourth minus T2 to the fourth power, where A is the surface area of the first body. T1 is the temperature of the first body in degree Rankine, and T2 is the temperature of the second body in degree Rankine. So all but bodies above absolute zero temperature radiate some sort of heat because there is some sort of molecular motion. Remember, earlier we said that temperature is kinetic energy, and kinetic energy is the energy. Okay, so if there is any motion, the body can give off some radiant heat. So the sun and the earth, they both radiate heat towards each other. And this seems to violate the second law of thermodynamics, which says that heat cannot flow from a cold body to a hot body. And so this is resolved by the fact that each body must be in the direct line of sight of the other to receive radiation from it. Therefore, whenever a cool body is radiating heat to a hot body, the hot body is also radiating heat to the cool body. And so since the hot body will radiate more heat due to a higher temperature than the cold body, the net flow still goes from hot to cold, keeping it in line with the second law of thermodynamics. And so that second law is still satisfied due to the fact that the net flow is still hot to cold. Emissivity, real objects don't radiate as much heat as the perfect black body. They radiate less heat than a black body, and they're called gray bodies. And to take into account the fact that real objects are gray bodies, we look at this following equation where Q is equal to epsilon sigma A T to the fourth, where epsilon is the emissivity of the gray body and epsilon is dimensionless. So emissivity is simply a factor by which we multiply the black body heat transfer to take into account that the black body is the ideal case. So emissivity is dimensionless and has a maximum value of 1. It has a maximum value of 1. Radiation configuration factor, radiant heat transfer rate between two gray bodies is calculated by using the equation Q is equal to F sub A times F sub E, sigma A in parentheses times T1 to the fourth minus T2 to the fourth. Where F sub A is the shape factor, and it depends on the spatial arrangement of two objects. And so how things are arranged in space, the way we like to think about it is like H2O. For me, it kind of looks like a little Mickey Mouse. You have the oxygen, and then down here on the sides, you have, the hydrogens are there, but they're kind of bent. Okay, so they're not sitting out here with the oxygen. They're actually kind of bent. So this is how these objects are arranged in three-dimensional space. If you think about an ice cube, because of the spatial arrangement or the arrangement in three-dimensional space, volume actually expands because they have those Mickey Mouse things, the O and the two H's, they have to arrange themselves so that oxygen is always near hydrogen and hydrogen is always near oxygen. So we're just talking about how things bend or contort so that they can occupy space. So F sub A is the shape factor. It depends on the spatial arrangement of two objects. F sub E is the emissivity factor, and that depends on the emissivities of the two objects. And so the two separate terms, F sub A and F sub E, can be combined given the symbol of F. And the heat flow between two gray bodies can now be determined by the following equation. Okay, so you combine FA and FE into just F. So Q is equal to F sigma A times T1 to the fourth power minus T2 to the fourth power. Okay, so the symbol F is the radiation configuration factor. And it takes into account the emissivity of both bodies and their relative geometry. And we just talked about one example of geometry. So water has this sort of bent geometry, okay, in three-dimensional space. And the radiation configuration factor is usually found in textbooks for a given situation. So those are constants. Okay, so we went through tables of, we went through several equations where the value was already given. Okay, and so they're saying that this is also a given value. All right, so one configuration, once this the factor is obtained, the overall net heat flux can then be determined. Radiant heat flux should only be included in a problem when it is greater than 20% of the problem. So they give you an example to calculate the radiant heat between the floor, which is a 15-foot by 15-foot floor of a furnace, and the roof if the two are 10 feet apart. And the floor and the roof temperatures are 2000 degrees Fahrenheit and 600 degrees Fahrenheit respectively. And you need to assume that the floor and the roof have black surfaces. So A sub 1 and A sub 2, or A1 and A2, is 15 by 15, and that's 225 feet squared for A1 and A2. T1, they converted degrees Fahrenheit to Rankine by adding 460 to each of those temperatures. So T1 is 2,460 degree Rankine. T2 is 1,060 degree Rankine. Okay, and the F, which is supplied from the book for this particular scenario, is 0.31. Again, some values are constants. They're already previously calculated because they've been experimentally determined. They worked on this and they've always gotten the same number, which is 0.31, okay? So this would be something that you would be able to look up. Q is equal to sigma AF times T1 to the fourth power minus T2 to the fourth power. Then they substitute in, so 0.174 BTU per hour foot squared Rankine to the fourth power, times 225 feet squared, times that F, which is 0.31, that's the given value, times 2,460 raised to the fourth power minus 1,060 raised to the fourth power. And so they come up with a Q of 4.29 times 10 to the 14 BTUs per hour. Okay, so take a moment and write out any equations that you have from this chapter on the summary page for your book, because you're going to need it. So make sure you go ahead and write those equations down. So we talked about heat transfer, we talked about conduction, we talked about convection, we talked about radiant heat energy. Now we're going to talk about heat exchangers, and they are devices that are used to transfer this thermal energy from one fluid to another without mixing the two fluids, okay? So if you think about, for example, a calorimeter, the example that I gave you, and you have like all of these ingredients for your ice cream, and on the outside you have ice, These two things, they don't mix, but the energy is pulled from that liquid until that mixture is actually frozen, okay? And so that's the way we like to think about heat transfer without mixing the two substances. So the objectives of this particular chapter is to describe the difference in the temperature profiles for counterflow and parallel flow heat exchangers, describe the differences between regenerative and non-regenerative heat exchangers, give the temperature change across a heat exchanger. They want you to be able to calculate the log mean temperature difference for the heat exchanger, and given the formulas for calculating the conduction and convection heat transfer coefficient, calculate the overall heat transfer coefficient of a system. So the transfer of thermal energy between fluids is one of the most important and frequently used processes in engineering. And so the transfer heat is usually accomplished by means of a device known as a heat exchanger. The common applications of this in the nuclear field include boilers, fan coolers, cooling water heat exchangers, which you do see a lot, and then condensers. So the basic design of a heat exchanger, normally there are two fluids and they have different temperatures, okay? And they're separated by some conductive medium. So for example, I like to think about a conductive medium like some sort of metal, something that can, hold the temperature and release the temperature. So when, something like copper or, one of these like precious metals, they tend, so they like to hold the heat and then give the heat away. So I like to think of those as being conductors. And of course, when you start thinking about electricity, then also understand that, metals are great conductors. And then there's some types of materials like resins and things like that are as good conductors as like a metal, right? So they don't like to take heat on and give heat off without damaging the resin, for example. So the basic, so the basic design of a heat exchanger normally has two fluids with different temperatures separated by this conductive medium. And the most common design has one fluid flowing through metal tubes and another fluid flowing around those tubes, okay? And on one side of either tube, the heat is transferred by convection, and heat is transferred through the tube wall by conduction. So heat exchangers, they are divided by several categories or classifications. Most commonly used type of heat exchanger, two fluids of different temperature flow in spaces separated by a tube wall. They transfer heat by convection and by conduction through the wall. And this type is referred to as an ordinary heat exchanger as compared to the other two types that are classified as regenerators or cooling towers. And so the ordinary heat exchanger is single phase or two phase. The single phase heat exchanger, both of the fluids are cooled and heated. So both of the fluids remain in their initial gaseous or liquid state. In a two-phase exchanger, either of the fluids changes phase during that heat exchange process. So in a steam generator and a main condenser in nuclear facilities, those would be considered to be two-phase heat exchangers, okay? Those would be considered to be two-phase. So so this is the ordinary heat exchanger classification. So single phase heat exchangers are usually of the tube and shell type, and that is the exchanger consists of a set of tubes in a container called a shell. Okay, and at the ends of the heat exchanger, the tube side fluid is separated from the tube side is separated from the shell side fluid by a tube sheet. And the design of the two-phase exchanger is essentially the same as that of a single-phase exchanger. Okay, so the difference between them is the phases of the fluid. Parallel and counterflow designs, although ordinary heat exchangers may be extremely different in design and construction, and they may be single or two-phase type, their modes of operation and their effectiveness is determined by the direction of fluid flow within the exchanger. The most common arrangement of fluid flow paths within a heat exchanger are counterflow and parallel flow. So a counterflow is one in which the direction of the flow of one of the working fluids is opposite of the flow of the other fluid. In parallel flow exchanger, both fluids in the heat exchanger flow in the same direction. So the figure 9 represents the directions of fluid flow in the parallel and counterflow exchangers. Under comparable conditions, more heat is transferred in a counterflow arrangement than in a parallel flow heat exchanger. Okay, so that's what we're showing. So they're using the arrows to show you that the flow is in the same direction here in the parallel flow exchanger, and the counterflow, they're using this pictorial representation to show you that you have flow circulation. So the temperature profiles of the heat exchanger indicate two major disadvantages in the parallel flow design. First, the large temperature difference at the ends causes large thermal stresses. The opposing expansion and contraction of the construction materials due to diverse fluid temperatures can lead to eventual material failure. Second, the temperature of the cold fluid exiting the heat exchanger never exceeds the lowest temperature of the hot fluid. And this rate relationship is a distinct disadvantage if design's purpose is to raise the temperature of the cold fluid. So the design of the parallel heat flow exchanger is advantageous because the two fluids are required to be brought to nearly the same temperature. The counterflow heat exchanger has three significant advantages over the parallel flow design. First, the more uniform temperature difference between the two fluids, it minimizes the thermal stress through the exchanger. And second, the outlet temperature of the cold fluid can approach the highest temperature of the hot fluid, or the inlet temperature. And then third, the more uniform the temperature difference, it produces a more uniform rate of heat transfer throughout the heat exchanger. So whether parallel or counterflow, heat transfer within a heat exchanger involves conduction and convection. One fluid convectively transfers heat to the tube wall, where conduction takes place across the tube to the opposite wall. The heat is then convectively transferred to the second fluid. So because this process takes place over an entire length of the exchanger, the temperature of the fluids as they flow through the exchanger is not generally constant. You know, it varies over the entire length, and that's indicated in the figure below. So the rate of heat transfer varies along the length of the exchanger tubes because its value depends on the temperature difference between the hot and the cold fluid at the point that you're looking at. Okay. So non-regenerative heat exchanger, this so applications of heat exchangers are classified as either regenerative or non-regenerative. The non-regenerative is the most frequently design use, and it involves two separate fluids. One fluid cools or heats, and the other with no interconnection between the two fluids. Heat is then removed from the hotter fluid and usually rejected to the environment or some sort of heat sink. The regenerative heat exchanger uses the fluid from a different area of the same system for both hot and cold fluids. The example of both regenerative and non-regenerative heat exchangers working in conjunction is commonly found in a purification system of a reactor facility. The primary coolant to be purified is drawn out of the primary system, is passed through the regenerative heat exchanger, non-regenerative heat exchanger, demineralizer, and then back through the regenerative heat exchanger, and then it's returned to the primary system. In the regenerative heat exchanger, the water returning to the primary system is preheated by the water entering the purification system, and this accomplishes two objectives. First, you minimize the thermal stress in the primary system piping due to cold temperature of the purified coolant being returned to the primary system. And then second, you reduce the temperature of the water entering the purification system prior to reaching the non-generative regenerative heat exchanger, allowing the use of a smaller heat exchanger to achieve the desired temperature of purification. The primary advantage of the regenerative heat exchanger application is conservation of system energy, and that is less loss of system energy due to the cooling of the fluid. And then we'll talk about cooling towers. The typical function of a cooling tower is to cool the water of a steam power plant by air that is brought into direct contact with water. The water is mixed with vapor that diffuses from the condensate into the air, and the formation of vapor requires a considerable removal of internal energy of water, and the internal energy becomes latent heat of vapor. Heat and mass exchange are coupled in the process, which is a steady state process, like the heat exchange in the ordinary heat exchanger. Wooden cooling towers are sometimes employed at nuclear facilities and in factories of various industries, and they generally consist of large chambers loosely filled with trays of similar wooden elements of construction. The water to be cooled is pumped to the top of the tower, where it's distributed by spray or wooden troughs. It then falls through the tower, splashing down from deck to deck, and a part of it evaporates into the air that passes through the tower. The enthalpy needed for the evaporation is taken from the water and then transferred to the air, which is heated while the water cools. Airflow is either horizontal due to wind currents or cross flow, or vertically upward in a counterflow to the water that's falling. And counterflow is caused by the chimney effect of the warm, humid air in the tower, or by the fans at the bottom or at the top of the tower. So mechanical draft towers are more economical and smaller in size than natural convection towers of this, they have the same cooling capacity. So in order to solve certain heat exchanger problems, a log mean temperature difference, LMTD, or delta T sub LM must be evaluated before heat removal from the heat exchanger is determined. And the following example shows this calculation. So the example is a liquid to liquid counterflow heat exchanger is used as part of an auxiliary system at a nuclear facility. The heat exchanger is used to heat a cold fluid from 120 degrees Fahrenheit to 310 degrees Fahrenheit. And assuming that the hot fluid enters at 500 degrees Fahrenheit and leaves at 400 degrees Fahrenheit, calculate the log mean temperature difference for the exchanger. So delta T sub 2 is 400 minus 120, so that's 280 degrees Fahrenheit. Delta T1 is 500 minus 310, which gives you 190 degrees Fahrenheit. So delta T sub LM is equal to delta T2 minus delta T1 divided by the natural log of delta T2 divided by delta T1. So they plug in and solve 280 minus 190 divided by the natural log of 280 divided by 190. And so the delta TLM is 232 degrees Fahrenheit. So the solution to the heat exchanger problem is simple enough to be represented by a straightforward overall balance, or it may be so detailed that it requires calculus, okay? And so, like I said, you can always take thermodynamics up a few notches by bringing in what you know about integration, what you know about, calculus 2 and calculus 3, what you know about partial derivatives. So you can definitely take this up a couple notches. A steam generator, for example, can be analyzed by an overall energy balance from feed water inlet to steam outlet, in which the amount of heat transfer can be expressed simply as Q is equal to M delta H, where M is the mass flow rate of the secondary coolant and delta H is the change in enthalpy of the fluid. Okay, so make sure you highlight this equation, and of course, when they explain it again. So the same steam generator can also be analyzed by energy balance on the primary flow stream using this equation. Q is equal to MC delta T, where M, CP, and delta T are the mass flow rate. C is the specific heat capacity, and delta T is the temperature change of the primary coolant. Okay. So this is laid out just a little bit differently than what you've seen for the equation. So make sure you highlight here and make sure you highlight here. Okay. And so they're giving you these variables respectively for this equation here. They're giving you these variables, the names for these variables respectively. So the heat transfer rate of a steam generator can also be determined by comparing the temperatures on the primary and secondary side of heat transfer characteristics of the steam generator using Q is equal to U sub 0, A sub 0, delta T sub LM. Condensers are also examples of components found in nuclear facilities where the concept of log mean temperature difference is needed to address the problems. When steam enters the condenser, it gives up its latent heat of vaporization to the circulating water and changes the phase to a liquid. Because condensation is taking place, it's appropriate to turn this latent heat of condensation. And after the steam condenses, the saturated liquid, it will continue to transfer some heat to the circulating water system as it falls to the bottom of the hot wheel, of the condenser. The continued cooling is called subcooling and is necessary to prevent cavitation in the condensate pump. So the solution to a condenser problem is approached in the same manner as those for steam generators, which is shown by this example. So overall heat transfer coefficient, when you deal with heat transfer across heat exchanger tubes, and overall heat exchanger coefficient, U, so W must be calculated. Earlier in this module, we looked at a method for calculating U sub zero for both rectangular and cylindrical coordinates. Since the thickness of the condenser tube wall is so small and the cross-sectional area for heat transfer is relatively constant, then you can use this equation U sub zero is equal to 1 over divided by 1 over H delta R over plus delta R over K plus 1 over H sub 2. Okay, so make sure you highlight the exceptions. Okay, so the thickness is really small and the cross-sectional area is constant. So make sure you highlight this one. So, you know, whenever you study thermodynamics, the exceptions or the conditions is the most important way to direct you to use a particular equation. So when you do see those, make sure that you highlight it. So the example is referring to the convection section of this manual. Calculate the heat rate per foot of tube from a condenser under the following conditions. Delta T LM is equal to 232 degrees Fahrenheit. The outer diameter of the copper condenser is 0.75 inches with a wall thickness of 0.1 inch. Assume the inner convective heat transfer coefficient is 2000 BTU per hour foot square degree Fahrenheit, and the thermal conductivity of copper is 200 BTU per hour foot degree Fahrenheit. And the outer convective heat transfer coefficient is 1500 BTU hour foot square, BTU per hour foot square degree Fahrenheit. And so they plug in and solve. Okay, so U is equal to 1 divided by 1 over H1 plus delta R over K plus 1 over H2. And then they put in a conversion factor as well because they need to convert from inches to foot. Okay, so 1 divided by 1 over 2000 plus 0.1 inch over 200 times that conversion factor, there's 12 inches in a foot, plus 1 over 1500 gives you a U0 of 827.6 BTU per hour foot square degree Fahrenheit. Then now that you have that U, you can also go into the equation for Q, which is Q is equal to U sub 0, A sub 0, delta T LM, Q over L, so they divided both sides by L, is equal to U 0, A 0, delta T LM. So this is all a derivation. Okay, this is all a derivation. And so they're giving you a final equation of U sub 0. I'm sorry, Q is equal to U sub 0, 2 pi R times delta T L sub M. Okay. So they're giving you a final equation. And so what they do is they plug in and solve. So this is the equation that you actually use. 826, which is previously calculated, BTU per hour, foot squared, degree Fahrenheit, times 2 pi times 0.375 inches. And then they multiplied it by the conversion factor, 1 foot over 12 inches times 232 degrees Fahrenheit to give you a value of 37,700 BTU per hour foot. And so take your time and put your equations on this summary sheet. Recording in progress. So we talked about the different methods of heat transfer. Now we're going to talk about heat generation and power input in a reactor. They're related. The reactor power is related to the mass flow rate of the coolant and the temperature difference across the reactor core. So some objectives for this particular chapter is to describe power generation process in a nuclear reactor core and the factors that affect power generation. Then describe the relationship between temperature, flow, power, and during the operation of a nuclear reactor. Define the following terms in this chapter: nuclear enthalpy rise, hot channel factor, average linear power density, nuclear heat flux, hot channel factor, heat generation rate of a core, and volumetric thermal surface strength. Then, of course, calculate the average linear power density for an average reactor core fuel rod. Describe a typical reactor core axial and radial flux profile, and then describe a typical reactor core fuel rod axial and radial temperature profile. So heat generation in a nuclear core is directly proportional to the fission rate of a fuel and a thermal neutron flux present. On a straight thermodynamic basis, this same heat generation is related to the fluid temperature across the core and the mass flow rate of the fluid passing through the core. Thus, the size of the reactor core is dependent upon and limited by how much liquid can be passed through the core to remove the generated thermal energy. So heat generation. I have to delete that part. So heat generation of a nuclear core is directly proportional to the fission rate of the fuel and thermal neutron flux. So on a straight thermodynamic basis, this same heat generation is also related to the fluid temperature difference across the core and the mass flow rate of the fluid passing through the core. Thus, the size of the reactor core is dependent upon and limited by how much liquid can be passed through the core to remove the generated thermal energy. Many of the factors that affect the amount of heat generated within the core, but its limiting generation rate is based upon how much energy can safely be carried away from the coolant. So the fission rate within a nuclear reactor is controlled by 7 factors: the density of the fuel and the neutron flux and the type of fuel all affect the fission rate. therefore the heat generation rate. So the following equation presented here to show how heat generation rate Q is related to these factors in the terms that are discussed in more detail in the nuclear science modules. So Q is equal to G in sigma. So Q is equal to G in sigma sub F phi V sub F, where Q is the heat generation rate in BTU per second. G is the energy produced per fission in BTU per fission. N is the number of fissionable fuel nuclei per unit volume, and that's in atoms per centimeter cubed. Sigma sub F is the microscopic fission cross section of the fuel, and that's in centimeters squared. Phi is the neutron flux, and that's in N per centimeter squared second. And then V sub F is the volume of the fuel, and that's in centimeters cubed. So the thermal power produced by a reactor is directly related to the mass flow of the reactor coolant and the temperature difference across the core. The relationship between power, mass, flow rate, and temperature is represented by this equation. Q is equal to MC delta T, where Q is equal to the heat generation rate in BTU per hour. M is the mass flow rate in pound per mass per hour. CP is the specific heat capacity of the reactor coolant system. That's in BTU per pound per mass per degree Fahrenheit. And delta T is the temperature difference across the core, which is in degrees Fahrenheit. So for most types of reactors, boiling water excluded, the temperature of the coolant dependent upon the reactor power and the coolant flow rate. If the flow rate is constant, the temperature will vary directly with power. If power is constant, the temperature will vary inversely with the flow rate. So once the type and the amount of fuel is determined, the shape of the neutron flux distribution along the core is established. Both radial and axial flux distributions must be determined. A radial distribution looks at flux from one center of the core out to the edges. An axial distribution looks at flux from the bottom to the top of the core. And as seen in equation 214, the fission rate directly affects the heat generation rate within a reactor core. And in the core regions of the highest flux, the highest heat generation rate is present. So many factors affect the axial and radial flux distribution, including the number and type of control rods, the geometry and the size of the core, the concentration of the fission product poisons, and the reflector properties. So the peak power production regions within each distribution normally occurs near the center of the core, as indicated by these two figures, 14 and 15. But they can vary during transients or as the core ages. So the above figure represents neutron flux profiles without considering the effects of control rods. Once the control rods and the reflectors are taken into account, the flux profile becomes much flatter, although the peak is, it still occurs near the center. So the shape of the profiles can be determined by measuring the ratio of peak flux to the average flux of, in the distribution. The peaking factor is referred to as the hot channel factor, and a hot channel factor of 1.0 would imply a flat flux profile. So thermal limits. So hot channel factors are calculated values used to take into account various uncertainties in tolerances used in core manufacturing. For example, consider a coolant channel of the maximum acceptable width and length that happens to be adjusted to a fuel plate with the maximum acceptable fuel loading. In this channel, you'll now have less water than in the average channel, receiving more heat than the normal coolant channel. And so for any given values of core power and flow, this hypothetical channel would be the closest to the thermal unit. Therefore, all design considerations are based upon hot channel factor for each core, and the nuclear heat flux hot channel factor, HF, HCF, is the ratio of the maximum heat flux expected at any area to the average heat flux for the core. Nuclear enthalpy rise hot channel factor is the ratio of the total kilowatt heat generation along the fuel rod with the highest total kilowatt to the total kilowatt of the average fuel rod. Thus, the limitation of the peak flux value in a core is directly related to the hot channel factor. However, in discussing flux profiles, average values of flux in the core are usually referred to rather than peaks. Okay, so in nuclear reactors, the fuel is usually distributed in the individual components, which sometimes resemble rods, tubes, and plates. And it is possible to determine the average power produced per unit length of fuel component by dividing the total thermal output of the core by the total length of all the fuel components of the core. This quantity is called the average linear power density, and common units for measuring average linear power density is kilowatts per feet. Okay, and so they give the question, calculate the average linear power density for an entire core if a 3400 reactor operating is operating in full power. Okay, so the core data is each fuel rod is 12 feet long. We have 264 rods per fuel assembly and 193 fuel assemblies in the core. Average linear power density is equal to total thermal power over total rod length. So average linear fuel power winds up being 3.4 times 10 to the 6 kilowatts divided by 12 times 264 times 193, which gives you an average linear power density of 5.56 kilowatts per feet or per foot. So the maximum linear power density when compared to the average linear power density results in the definition of the nuclear heat flux hot channel factor. And this nuclear heat flux hot channel factor can be looked at as having axial and radial components that are dependent upon power densities, and thus the flux in the radial and axial planes of the core. Once the hot channel factor is known, the maximum local linear power density anywhere in the core can be determined and, as demonstrated in this example. So if you have a nuclear heat flux hot channel factor of 1.83, calculate the maximum local linear power density in the core for the previous example. So this is maximum linear power density is equal to HF HCF times AV linear power density. And so they multiply 1.83 times the previously calculated value, which is 5.56 kilowatts per foot. And they wind up with a maximum linear power density of 10.18 kilowatts per foot. Okay, so that second equation. Normally, nuclear facility operators are provided with the above core power and heat generation distributions rather than having to calculate them. In addition, various monitoring systems are always employed to provide the operator with a means of monitoring core performance and the proximity of the existing operating conditions to core operational limitations. Additional areas of interest are the temperature profiles found within the core. A typical axial temperature profile of a coolant channel for a pressurized water reactor, PWR, is shown in figure 16. As would be expected, the temperature of the coolant will increase throughout the entire length of the channel. However, the rate of increase will vary along with the linear heat flux of the channel. The power density and the linear heat rate will follow the neutron flux rate. However, the temperature distributions are skewed by the changing capacity of the coolant to remove the heat energy. And since the coolant increases in temperature as it flows up the channel, the fuel cladding and thus the fuel temperatures are higher in the upper axial region of the core. So a radial temperature profile across a reactor core, assuming all the channel coolant flows are equal, will basically follow the radial power distribution. And the areas with the highest heat generation power rate, the areas with the highest generation rate, which is power, will produce the most heat and have the highest temperature. A radial temperature profile for an individual fuel rod and coolant channel is shown in figure 17. And the basic shape of the profile will be dependent upon the heat transfer coefficient of various materials involved. And the temperature across each material will have to be sufficient to transfer the heat that is produced. Therefore, if we know the heat transfer coefficient for each material and heat flux, we can calculate the fuel temperatures for a given coolant. Volumetric thermal source strength. The total heat output of a reactor core is called the heat generation rate. The heat generation rate divided by the volume of the fuel would be given, will give the average volumetric thermal source strength. And the volumetric thermal source strength may be used to calculate the heat output of any section of fuel rod, provided the volume of the section is known. So volumetric thermal source strength is equal to Q for the core divided by the V of the fuel. So you need that. During the operation of a nuclear reactor, physical changes occur to the fuel that affect its ability to transfer heat of the coolant. The exact changes that occur are dependent upon the type and form of fuel. Some reactors use fuel assemblies that consist of zircaloy tubes containing cylindrical ceramic pellets of uranium dioxide. And during manufacture, a small space or gap is left between the fuel pellets and the zirc alloy tube or clad. And this gap is filled with pressurized helium. As the reactor is operated at power, several physical changes occur in the fuel that affect the gap between the pellets and the clad. And one change occurs due to high pressure in the coolant outside the clad and the relatively high temperature of the clad during the reactor operation. The high temperature and high pressure causes the clad to be pushed in on the pellets by a process referred to as creep. Another physical change is caused by the fission process. Each fission event creates two fission product atoms from a fuel atom. And even though each fission product atom is roughly half the mass of the fuel atom, the fission products take up more volume than the original fuel atom. Fission products that are gases can collect together and form small gas bubbles within the fuel pellet, and these factors cause fuel pellets to swell, expanding them out against the clad. So the two processes of pellet swell and clad creep both work to reduce the gap between the fuel and the clad. And this change in the gap between the pellet and the clad has significant impact on heat transfer from the fuel and the operating fuel temperatures. Initially, a significant temperature difference exists across a gap to cause heat transfer to take place by convection through helium gas. As the size of the gap is reduced, a smaller temperature difference can maintain the same heat flux. And so when the fuel pellets and the clad come in contact, heat transfer by conduction replaces convection, and the temperature difference between the fuel source and clad, it decreases even more due to processes of the pellet swell and clad creep. The fuel temperatures of some reactors decrease slightly over time, while heat flux from fuel and therefore power reactor, they remain constant. So not all changes that occur into the fuel during the reactor operation work to enhance fuel transfer. So if the chemistry of the coolant is not carefully controlled within the appropriate limits, chemical reactions can take place on the surface of the clad, resulting in the formation of a layer of corrosion or crud between the metal of the clad and the coolant. Typically, this layer will have a lower thermal conductivity than that of the clad material, so it will act as an insulating blanket, reducing heat transfer. And so if the corrosion layer is allowed to form, a larger temperature difference will start to be required between the coolant and the fuel to maintain that same heat flux. Therefore, operation at the same power level will cause higher fuel temperatures after the buildup of the corrosion products and crud. So take a moment to notate any formulas on your summary sheet here. So we talked about a few different methods of heat transfer. And now we're going to talk about decay heat. So decay heat production is a problem associated with nuclear reactors. Even though the reactor is shut down, the heat produced from the decay of fission fragments and the limits for each particular reactor are established to prevent damage to fuel assemblies due to decay heat. So like I said, those the components like uranium, they continue to decay. And as they decay, they continue to give off heat. And so that's what they're describing here. So define the term decay heat. Given the operating conditions of the reactor core and the necessary formulas in this chapter, the objective is to calculate the core decay heat generation, and then describe two categories or methods for removing decay heat from a reactor core. So a problem peculiar to power generation by nuclear reactors is that of decay heat. In fossil fuel facilities, once the combustion process is halted, there is no further heat generation, and only a relatively small amount of thermal energy is stored in the high temperature of plant components. In a nuclear facility, the fission of heavy atoms such as isotopes of uranium and plutonium results in the formation of highly reactive fission products. And these products radioactively decay at a rate determined by the amount and type of radioactive nuclides present. And some of these radioactive atoms, they'll decay while the reactor is operating, and the energy released by their decay will be removed from the core along with the heat produced by the fission process. So all radioactive materials that remain in the reactor at the time it is shut down and the fission process halted will continue to decay and release energy. And the release of energy by the decay of fission is called decay heat. And the amount of radioactive materials present in the reactor at the time of shutdown is dependent upon the power levels at which the reactor operated and the amount of time spent at those power levels. And so the amount of decay is very significant. Typically, the amount of decay that will be present in the reactor immediately following the shutdown is roughly 7% of the power level that the reactor operated at prior to shutdown. And a reactor operating at 1,000 megawatts will produce 70 megawatts of decay heat immediately after shutdown. And so this amount of decay heat produced in the reactor will decrease as more and more radioactive material decays to some stable form. Decay heat may decrease to about 2% of the pre-shutdown power level within the first hour and 1% within the first day. Decay heat will continue to decrease after the first day, but it will increase at a much slower rate. And decay heat will be significant weeks and even months after the reactor is shut down. So the design of the reactor must allow for the removal of this decay heat from the core by some means. And if adequate heat removal is not available, decay heat will increase the temperatures in the core to the point that the fuel melting and the core damage will occur. And fuel that has been removed from the reactor core will also require some method of removing decay heat if the fuel has been exposed to a significant neutron flux. So each reactor facility will have its own method of removing decay heat from both the reactor core and also any irradiated fuel removed from the core. And so, So the amount of decay heat being generated by a fuel assembly at any time after shutdown can be calculated in two ways. The first way is to calculate the amount of fission products present at the time of shutdown. And this is a fairly detailed process and it's dependent upon the power history. For a given type of fuel, the concentrations, the decay energies, the half-life of fission products are known. By starting from a value based on the power history at shutdown, the decay heat generation is can be calculated for any time after shutdown. And so the exact solution takes into account the fact that there are hundreds of different radionuclides present in the core, each with its own concentration and decay half-life. And it's possible to make a rough approximation by using single half-life that represents the overall decay of the core within a certain period of time. And the equation used is Q is equal to Q0 times 1/2 raised to the power of time divided by half-life, where Q is the decay heat generation rate at some time after shutdown. Q0 is the initial decay heat immediately after shutdown. T is the time since shutdown, and half-life is the overall decay half-life of the core. Go back. So they asked the question, if you have a 250 megawatt reactor and it has an unexpected shutdown, from the data supplied from the vendor, we know that decay heat time of shutdown will be 7% of the effective power at the time of shutdown, and it will decrease with a 1 hour half-life. So the effective power at the time of shutdown is calculated to be 120 megawatts. How much heat removal capability in BTU per hour will be required 12 hours after shutdown? So first, you have to determine the decay heat immediately following shutdown. And that's done by multiplying 120 by 0.07 for that 7%. They made it a decimal. And so you have an 8.4 megawatt decay heat shutdown. And then you use equation 215 to determine the decay heat at 12 hours later. So Q is equal to Q0 times 1/2 raised to the time over half-life. And then they substitute in. So for Q, they have 8.4, which you calculated up here, times the 1/2 raised to the 12 hours divided by 1 hour. Okay, and this was 1 hour. Let's get it. And then you wind up with 2 times 10 to the minus third megawatt times 3.413 times 10 to the 6 BTU per hour divided by 1 megawatt. And so your Q winds up being 7,000 BTU per hour. So the second method is simpler to use, but it's not useful for forecasting heat loads in the future. To calculate decay heat load at a given point after shutdown, secure any heat removal components from the primary system or spent fuel and plot the heat up rate. If the mass of the coolant and the specific heat of the coolant is known, the heat generation rate can be calculated accurately by using Q is equal to MC delta T over delta lowercase t for time, where Q is the decay heat, M is the mass of the coolant in pound per mass, CP is the specific heat capacity of the coolant, delta T is the temperature change of the coolant in degrees Fahrenheit, and the lowercase delta T is the time over which the heat up takes place in hours. So an example problem is 3 days after a planned reactor shut down, it is desired to perform maintenance on one of the two primary heat exchangers. Each heat exchanger is rated at 12,000 BTU per hour. To check the current heat load of the primary system due to decay heat, cooling is secured to both heat exchangers. The primary heats up at a rate of 0.8 degree Fahrenheit per hour. The primary system contains 24,000 pound per mass of coolant with a specific heat capacity of 0.8 BTU per pound per mass degree Fahrenheit. Will one heat exchanger be sufficient to remove any decay heat? And so the equation that's used for this particular problem is Q is equal to MC delta T divided by delta lowercase t. And then they plug in and solve. So M is 24,000 pound per mass times 0.8, which is your specific heat capacity, and that's in BTU per pound per mass degree Fahrenheit. And then the delta T is 0.8 degrees Fahrenheit per hour. Okay. So the Q winds up being 15,360 BTU per hour. So one heat exchanger removes 12,000 BTU per hour. And so they're going to compare the value calculated to see that one heat exchanger is not efficient because it doesn't remove 15,360 BTU per hour. So this one heat exchanger at 12,000 BTU is not sufficient when you compare these together. So the decay heat limits, you have a reactor decay heat can be a major concern in worst case scenarios. It can cause melting or damage to the reactor core, as in the case of 3 Mile Island. So the degree of concern with decay heat will vary according to the reactor type and its design. And there is little concern about core temperature due to decay heat for a low power full type reactor. Each reactor will have some limits during shutdown that are based on decay heat consideration. And these limits, they vary because the steam generator pressure, the core temperature, and any parameter that may be related to decay heat generation. So even during the refueling process, heat removal from expanded fuel rods is a controlling factor. And so for each limit developed, there is usually some safety device and protective feature that is established. Methods for removing decay heat from a reactor core can be grouped into two categories. One category includes the methods in which you circulate fluid through the reactor in a closed loop using some type of heat exchanger to transfer heat out of the system. The other category includes methods which operate in an open system, drawing in cool fluid from some source and discharging warmer fluid to some storage area or the environment. In most reactors, decay heat is normally removed by the same methods used to remove heat generated by fission during reactor operations. Additionally, many reactors are designed such that natural circulation between the core and either its normal heat exchanger or emergency heat exchanger can remove that decay heat. These are examples of the first category methods for decay heat removal. And if a reactor design is such that decay heat removal is required for core safety, but accidents are possible, and that will make the closed loop heat transfer methods described above unavailable, then an emergency cooling system of some sort will be included in the design. Generally, emergency cooling systems consist of some reliable source of water that's injected into the core at a relatively low temperature. The water, this water, is heated by decay, heat of the core, and exits the reactor via some path where it will either be stored in some structure or released to the environment. Use of this type of system is always less desirable than the use of the closed loop systems described above. And so they're saying that you should research systems, limits, and protective features at your own specific facility. So what you guys need to do now is make sure that you write any equations here on the summary. So I'll pause here and then we'll